in our 3-month journey on data structure and algorithms. As usual, I'm excited to be here. I don't take the opportunity for granted at all, because I just love being with people of like minds, people who share the same interests and passions. Okay, let me share my screen. So today we are looking at data structure and algorithm with focus on heap and hash. Okay. A good place to still start from is to put this in the proper context, that what we're talking about today is a continuation of our abstract data type. So those concepts, that is heap, hash, especially the heap aspect of it, is a data structure. Okay, by now you know what a data structure is or looks like. The simple way I like to describe it is the shape of things, the shape of your data. Okay, so heap follows from that sort of data organization. So because as we look at heap today, we will focus on their uses, the values they can store, and the set of operations that are optimized for that data structure. Okay, when we look at hash also, we will see relevant things. Okay, without much ado, we go into heap. Oh, let me also not forget to give a shout out to those people who have submitted the assignments and then posted them on the GitHub space. So thanks so much. Specific shout out to Adegoke. I think he or she goes by the name Ali Fatik, Gabriel, and then one other person, I can't remember the name now. Yeah, so to every one of you who have submitted so far, I'm not able to see all, but for everyone who have submitted so far, good job. Good job. That's actually the way to go. Because as we said earlier in the previous sessions, the more you attempt to work on these little exercises, the better you are at grasping the concepts. You are building your muscle memory. You are getting used to the pattern. You are understanding those theoretical aspects that are best understood when combined with practice. All right. So I encourage everyone to equally do that. You could go back to previous exercises and just do them because you need them in the algorithm section. Okay. With that said, heap. As usual, I would like to get your intuition about heap. What comes to your mind when you think about heap? If we look at you are free to type in the chat section what comes to your mind, what image, what picture, what does it remind you of? Okay, so feel free to type it in the chat. Let me see anything coming up in the chat. So what comes to your mind? All right, load, burden, good. Load of items, okay, good. Okay, yeah, load, body, load of items, Yeah, that's a data. That's data. A load of items, a collection. Okay, but what shape of the load or burden comes to your mind? Items stacked on top one another like a pyramid. Yeah, stacked on top of another. Yes, the word I don't like there is stack. Okay, you already discussed stack last week. So stack may not be the proper term to use here. Okay, it looks like a pyramid, yes. Dome shape, yes. Cone, yeah. It looks like a cone. It looks like a pyramid, yes. Okay, yeah. You see, it could really be a harmful trying to get a particular object in life to attach this concept to. Okay, but that is what you must try to do as you come across new concepts, even when not related to programming. That's how understanding is developed. Oh, okay. So, similar to what have been mentioned, heap could look like this. You could have an image of, yes, load of items, not necessarily stacked, okay, but they come in a shape that looks like a pyramid. Okay. Your landfill, uh, for I think we can all relate with a trailer load of sand at construction sites, right? Right? Yeah. Where you see construction workers, bricklayers come with tipper load and pour sand, gravel for construction. Yeah. Okay. You go to dunk sites, okay, or landfill, as it's called here, and you see something like this. You could also picture it as a tree-like shape, okay, tree-like shape, where it looks still similar to a tree, but as it goes down towards the bottom, it spreads out from a pointed space at the top. No, okay, so this kind of data or heap could also give you an intuition when you talk about genealogy, ancestral links, okay, or history. You look at your parents. From your parents, you could begin to build up to your grandparents, to your grand-grandparents. You keep building till you either get to Adam or you get to Lucy. So it all depends. No, okay, but this is the kind of structure that the heap data structure tries to mirror and then manage. And there are specific operations, as we'll see later on, that are optimized for this kind of structure. That is, when you spread out your data in this way, there are things you get cheaply. There are operations that will become fast. It may not be appropriate or optimized for some other operations, as we'll also see, but then that is the cost of choosing something like this. Okay, so going further into it, a heap is a data structure that is usually implemented with an array that can be thought of as a tree. This is a very simple explanation from Brilliant. Okay, I encourage everyone to look frequently at Brilliant. Okay, they've got good write-ups, topics that keep you mentally alert and informed. No, okay, so it's a data structure usually implemented with an array, okay, but is tree-like in shape, tree-like, and that is a very core description of a heap. When you hear the word heap, think of a landfill, think of a tree, think of a pyramid. Okay. So it will come in a shape like this. We'll look later on in these details. Okay. And the other important thing about this data structure. Okay, so though it can be implemented with an array, it can also be implemented with other complex type, like maybe a node, okay, or object, any other complex type, so to say. Okay, so not necessarily with an array, but most implementations of a heap structure is an array, and that makes sense, as we'll see later on. Okay, and if I remember correctly, at the beginning of this essay, I think that should be week 2 when we talked about array. We got to understand that array is an important data structure. Okay, very, very important, especially in being able to help us organize simple types like your car, int, okay, and then bool. Okay, you can organize and spread them out close together in memory. Okay, so array structure, very efficient, very fast in searching, in locating items. It has its drawbacks when it comes to adding and removing items, and of course the optimizations around that. Okay. Heap is a continuation of that optimization on a data on an array. Okay, so that is why it builds on it as an abstract data type. Okay, it builds on that structure. Okay, so we'll see where it becomes very, very important. One thing to know about array is when you store items in that array, you could decide to store your data in a particular order, maybe alphabetical order, lowest to greatest, okay, increase ascending or descending order. You could do that, or that order may not be appropriate for your specific use case or focus. So it may not be as simple as ascending order or descending order. Okay, what if you want to store them in a particular shape? What if your application needs a data structure that is, or that wants to mimic parent-child relationship, that want to mimic a pyramid structure, or that wants to mimic genealogy, ancestrally linked from Lucy or Adam to the present you. Okay, so at that point, you can still build where heap comes in, that you can build that kind of data structure on top of an array. All right, so it's a tree-like data structure, as we have mentioned, but they meet these conditions. These conditions are very, very important. A tree-like data structure, which is a heap, must be a binary tree. Some will say must be a complete binary tree. That is, there is the peak. At that peak, you have the root node or the root value. Okay, and that root value has subtrees or subnodes. Okay, that's its own direct children. Then each child has two subtrees, and that is how it begins to go and go to you get to the base. Okay, so it must be a binary tree. That's what we mean when we say it's a binary tree. And it has certain properties, more properties, like the parent node must either be greater or equal to all the child nodes or be less than all the child nodes. We'll see example of this. Okay, we say the tree is balanced when all the nodes, all the child nodes are filled out. Of course, they must conform to parent-child relationship. A node must have two. Okay, but at the base, they must be balanced. The left side and the right side must be filled out. Okay, except in some cases where, depending on the number of data you have a situation where a child or where a node has one child. So if you're going to add a new node, that space will be filled up, and then we'll see what happens. We'll see what happens to the tree or to the heap when you add or remove item, because part of the condition is that the tree must be balanced at all times. Okay, so this data structure is very optimized or efficient for this kind of scenario. Priority queue, you come across that word, priority queue. Priority queue gives a sense of order, ascendancy, that is not just based on the property of the value. Okay, it's not just ascending order or descending order. Probably you want certain object to be on top of another. The simple way of doing this currently, or the simple example of this, is to use numbers, as we see here, to use numbers to say, okay, in this case, the highest priority for this kind of heap is that the root node is greater than all of them. Yes, because we are dealing with numeric type here. 100 is bigger, is the greatest among all these numbers. So that's the heap property or the root node. Okay, followed by the next big numbers, then each having their next, okay, until it goes like that. Okay, so if you want to store that kind of priority where the earliest man should be on top, or the biggest number should be on top, or the most important thing or data should be on top, then heap is what you should look at. Okay, so it's just it's not only numbers. I need to emphasize that. Don't only think that it is meant for numbers. Okay, priority queue, that is the essence. Priority being an important term here. Okay. So again, building on that, for scenarios with least or highest priority, which we have seen, if you want to do that, you can use it to maintain order, okay, increasing, decreasing. This is very, very important for this data structure. It's usually very optimized, in fact, most optimized for finding minimum and maximum value in a collection. Okay, the cheapest operation you can get out of this data structure. Other kind of operation could be slower. For instance, is not optimized for search. Okay, not optimized for search, but very much optimized for minimum and finding minimum and maximum, what is at the beginning and what is at the end, the lowest and the highest. Okay. Insertion, deletion, yeah, pretty much fast because they are based on array. Okay, but then compared to this min and max, we can still say they are slower, which is why in the industry it is agreed that heap is slower than array or the linked list. But again, they are much more optimized for these scenarios. Okay, these scenarios of min and max, that is what they are meant for. And you see how they can be used. Yeah. So if we take a look further at it, remember we mentioned that they are based on array implementation. Okay, so take a look at this where you have a series of numbers. So this is your array, a list of items you want to store, ranging from 16, 14, 10, and then all the way to 2, 4, 1. So you want to store an item like this. For your particular scenario, it's not sufficient to just store them in ascending order or descending order, 1 to 16 or 16 to 1. Okay, you want to maintain priority. You want to maintain order, okay, as you store the data. You want the position in your array to mean priority. So the value with the highest priority is in the first position in your array. I'm using the word value rather than use the word number. Remember I said that it could be for numbers or any other data type. Okay, so think beyond just numbers. So if the first man or the first woman, whatever it is, should be first, of course, by using the word first, we'll put the first person here. All right. The last person, whoever that will be, the last person that will see everybody, that will see the end of the world, will be at this place. So that's some sort of a priority. So the position, we put the first person here, the children of the first person, their own children will come after that. You can see. So it does not simply go from top to down in how the data is spread out in your memory. Okay, that's in your computer memory. Okay, so you have 16. The subtrees of 16 will be 14 and 10. As you can see here, 16, you have 14 and 10. Then the subtrees of this will be this. The subtrees of this will be this. And if you look at it, the child nodes of the parent of the root node, both of them are bigger than all the children, okay, like all their cousins and nieces. Okay, so you can see that sort of relationship, and then this become bigger than this, bigger than this. So I like this illustration because it shows you that this kind of structure, pyramid structure, represented like a chain, okay, is stored in an array like this. So your data is already stored like this, because how else, if you think about it, if you're going to store this information, the priority information elsewhere. You will need more other kind of data, which means you use more space to store that extra information. Like say, okay, 16 should be in the first position, in the first index, 14 should be in the second index, 3 should be in the seventh index. You're going to use other memory. Your applications will take more memory to store that extra information. But with a heap data structure, you already spread out your data according to priority. And so there's the picture you have in your mind as you think about heap. Okay, and there's usually two conditions which we'll look at very soon, which is that, yes, the heap property, which is the root node, okay, can either be the value with the highest number or prominence or priority, or the one with the lowest. We'll see what they are called shortly. Yeah. So further properties of heap, remember in the context of ADT, note these terms. They are important when we talk about the heap data structure, your key, your heap. The child nodes are either called leaves, some will call them leaves, some will call them nodes, some call them subtrees. Heapify is a term you should also be aware of. Okay, you see what it means later as we go on. We already talked about they being top-down, okay, a top-down structure with minimum maximum element at the top. Okay, and then in creating this data structure, they are filled from the left to right. Okay, like if you have your root node and you're going to add a new node, you add it on the left if it's one. Okay, and then when you add the second one, you add here. Okay, then when you add the third one, you add it here. The fourth one, you add it here. Then that the fifth one, you add it. The sixth one, you go back to the child node of the root and then add it left. You got a new one, you add it here. So that is how it is filled, or at least this ensures that the tree is always balanced. So, okay, and as you remove from the trees or add, we heapify, we balance the tree. We've seen that it can be represented with an array. Okay. If we don't, you will say this a lot. It can also be represented in a database. Okay, a database can be built on this. So a database is a larger structure. It's a much more complex structure, but a database can be stored in a way to mirror this parent-child hierarchical relationship. Okay. So it's got a couple of formulas for detecting or managing the parent-child relationship. So the formula is that a parent is always on index I, whatever the position is. Okay, I can be any position here. So if you pick 9 as a parent, if I is 9, so 9 is a parent, and then that 9 will have to get to the subtrees or the children of 9. The formula to get that is this. This is constant, time-tested, generally approved formula. It works, okay, and it's efficient. You can't get anything more efficient than this. So to get to the left side, multiply I by 2 and then add 1 to it. that gives you the position of I. Add 1 to it to get to the left, to get to the right, add 2 to the multiplication. Okay, so note this. I will advise you to please do the exercise to get the intuition of this. Very, very important. It's simple, but you need to do it to really understand it. You will share also that, as we've mentioned, extremal elements, which is that mean and max is always at the root. Okay, so we mentioned this before. You can either have the maximum element or the minimum element at the root, which allow constant time access of big O of 1. Okay, so because if we know where the if the data is already arranged this way and you are asked for what is the highest number, depending on your kind of heap, you know where to pick it. You just do index of 0 or index of n minus 1. You get what you're looking for. So heapify is an important term. Okay, so heapify has to do with balancing your trees to ensure that they are always a complete binary tree, irrespective of operations that happen on there. So if you add a new item or remove an item, you always have to heapify. That is, you balance the tree. Balancing the tree involves, in the case of addition, taking the new value and then begin to compare with its parent and with the other parents, such that if the value is greater than its parent, then they may need to swap position. Okay, then you check again, is it greater than the parent of that parent? You swap position until it gets to that point in the tree or in the heap where it is not more than its parent. And if that is the root node, then it becomes the root node. The same thing with deletion. When you remove an item, you have to balance the tree again. And that is where the cost function is. This is where it becomes slower, okay, than a linked list, for instance. You know, remember in the discussion of the linked list, insertion and deletion is the fastest, is really very, very fast. Okay, so it still looks more like the array insertion and deletion headache, where after removing an array, an element of an array, you have to close some gap, rearrange everything. So this is what happens for a heap structure also. The two types of heap data structure will come across most times will be max and min heap. Max heap and then min heap. Okay, they are very, very similar. Okay, just to highlight it, we won't spend much about it. The difference is just that for a max heap, the value with the highest priority or number is on top. Whereas in the min heap, the value with the lowest number, okay, the value with the lowest number of priority is on top. Okay, and this is the formula. Parent of I is less than any index in your array. For a min heap, for a max heap, this is just the condition. Also, the element is greater than all other elements in the array. Okay, so it's just a simple switch or condition in your implementation to know whether you are dealing with a min heap or a max heap. Okay, okay, I'm going to show us this simple algorithm for Heapify. Okay, so this is a pseudo code. Okay, I'm introducing this here as some sort of preparation for algorithm. Okay, and just to highlight the importance of reading pseudocode, not just reading it, writing it also. A pseudocode is just a it's not a programming, it's not actual codes that are runnable or that can be run by a compiler. Okay, they are just simple definition or description of the steps involved in your particular operation or your logic. Okay, stepwise process taken to arrive at a complete implementation. So it's usually descriptive. You can use something similar. It could look so close to a programming language, valid statement, but not necessarily. So for you to balance a tree, a heapify function looks typically like this, where you have an array, the size of the heap or array, and then a particular index. Okay, so the algorithm states this way, that if you are going to balance the tree, first you make whatever index you are on, the particular point in your tree where you are, that is the index. Okay, make it the maximum. Get its left child with this formula. You can see the formula. Get the right child with this formula. Then do a comparison. Check to be sure that the left side is not above the heap size. Like it's just a bound check. Okay. Here you check if what is on that, the value in your height position, your index, okay, you check that is less than the left side. So if it is less, if I is less than his left child or his first child, in this case, you make marks to be left. Otherwise, it remains the same. Okay, this assumes a max heap, right? You check the same thing for the right. If the max, if what is currently on the max, in case it is this, all right, is greater than what is on the right, then you make the right side this. And then you check at the end that max is not, you check if max is not what is not I. Okay, if max is not what is on the height index, you do a swap. So there's not a particular implementation. This is just description that, okay, swap the items, make what is currently on the max to be what is on the height index, and what is on the height index will be on the max. Then this is a recursive function. So what it does here is then it calls the same function. Why does it have to call the same function? Because this operation needs to check the value for each node, all right, above the current index. Okay, to be just to be able to eventually do this swap position. Okay, if this is not true, there's no need to swap position, then you are at the right place. Okay, so you'll see a lot of implementation of this Heapify function in various language online. Please take a look at them. Okay, take a look at them. So this function is what is called after a change, an addition or a deletion of item on the heap. Okay, because of time, I will skip this slide. You'll go through it once we share it. Okay, it's just comparing those data types. Then the data operations that are very common or important when you talk about heap. Okay, this is very important. You should be able to easily get the minimum and the maximum elements. Okay, the heapify function, which is balancing the tree, inserting new element, deleting, searching, getting a heap size at the total number, decrease or increase key, and then heap sort. Okay, sorting the elements of a heap data structure. Remember that the elements in a heap are not sorted in storage. They are not sorted. So if you see it here, they are not sorted. Okay, so you may want to get a sort a sorted order of the items. Okay, because it's not inferred naturally in the position or in the indexing. So sorting is a common operation. You also see how it is done. Okay. In terms of the heap operation runtime complexity, the performance on the space complexity is pretty much constant, as you don't use auxiliary space. Okay, but in other activities or operations such as getting element, getting min and max has some complexity. So min and max, as we said, is the cheapest. Okay, very easy. Inserting is usually big O of log n. Okay, because in this case, you do not just insert into a position. After insert, you have to balance the tree, and balancing may require swapping elements. Okay, it's still efficient. At least it's log n. It is not big O of n. Okay, big O of log n is better than log n, because if you say if you get log, if the number of items is 100, for example, and you are looking at log of that number, log of 100 is just 2. Okay, log of 100 is 2. Log of 1000 is 3. Okay, log of 400 is about 2 point something. Okay, 2.3 or 2.4. Log of 500 is about 2 point something. So it's efficient in terms of reducing the number of loops or iterations that your code will run. Okay, much more better than running it 100 times. If it runs the operation 2 more times, that is better. Okay. Okay. So the only other one I think worth mentioning here would be the heap sort. Sorting a heap is a little more expensive. It's still better. It's still efficient if you are going to sort, because we're going to traverse the whole tree, right? And in traversing the whole tree, we'll swap position. So it goes through everything, which is why we have the n here multiplied by log n. Okay, so if your n is 100, based on the initial example, 100 multiplied by log of 100, which is 2. So that's 200. Okay, so for 100 item, 200. If your data scales from 100 to 400, okay, you still get 100 times 2 point something. So the difference is not really much. Okay, if your data scales to 600, it's still moving from 100 times 2 point something. Okay, so unlike if it is a quadratic uh, uh, time complexity, quadratic will mean the order of two times, 2 raised to power, it could be 2 times 2, or okay, n times 2, sorry. Okay, so imagine it's n times 2, 100 times 100 as your data increase, and n becomes 400. 400 times 400 is different from 400 times 2.3 or 2.4. So the heap sort is still an efficient data structure, okay, uh, for in this case. Uh, let's take a little break. Is there any question on this particular topic, heap? Any question?
If you have questions, just drop it on the comment section so we could take a
Okay.
look.
Okay. Is anyone? Let me see. Yes. Yes. N times n is worse than, yes, n log of n. Correct. N times n, n times n is worse. 100 times 100 is worse than 100 times 2.3. Okay. Yeah. The difference, it doesn't grow so much. So as your data increase until you get to a particular bound, when it get from 100, log of 100 is 2, log of 1003. Or okay, so you still have enough room. Your data, your system can still perform relatively well before it gets to that cutoff point where the number in the log, the factor increases significantly, jumping from 2 to 3, then 3 to 4. Okay, log of 10,000 will be about, we should be 10,000 should be about 4. Okay, so you could say that if your item is 2,000, the difference between the runtime experience from 2,000 to 10,000 is not much. So your data still grows very well. Okay, so we will move on. We'll move on from this. Uh, I don't think there's need to show code for this one. I wanted to, but because of time, we shouldn't. Rather, please, let's converge on our GitHub. I'm going to give exercise after this, so we interact over it. We see the implementation, and I don't mind. I can also post an implementation of the heap on either group chat or on the GitHub link. But I really want us to experiment with this. Oh, okay, that is what will give you the intuition and ultimately the understanding that you need for this thing. Okay, if we don't have much question again, any other question again, we quickly just go to the concept of hashing. Okay, so what comes to your mind when you think about hashing? You must have heard about the word before, I'm sure. But what does it remind you of? Let's see. You can type it in the chat. Let's see what comes up. Encrypt. Yes, that's correct. Encrypt. Yeah, it has application there. So it's a good thing to put in mind. Hashing, no, no. Encrypting more like it. Dictionary also, yes. Dictionary is good. Encrypt, good. A combination of different values and encrypting them, yes, is still good. Mhm. I like the word dictionary because it gives us a picture. Your Oxford dictionary, think of your Oxford dictionary or any other language dictionary you have at home. Uh, it could even be glossary or other reference books, encyclopedia, Britannica is a good example. Yeah. Key and value pairs, yes, that's also good. Yes, key value pair is good. Uh, so we have good suggestions so far. A technique, someone puts a technique used to map data to a fixed size array. Yes, called a hash table or a hash map. Yes, you've already given the definition. So we should end the conversation here and just go home. All right. Yes. So that's good. Hmm. So dictionary, put it to your mind. Then also think of you trying to locate objects in your house or at home. We've all been there. Where did I drop my phone? My keys, that pen. For your phone, you have to tell somebody, please, can you help me call my phone? Okay. When it rings, you get your phone. Okay. Uh, some people have this habit of mapping location or mapping items according to where they are placed at home. So let me explain that. Where some people drop a key on the table and then think of something like, okay, a table, a cycle, or a rectangle. So when they are looking for their key, they think of that concept, that object they are associated with that time or that place when they store the object. So when they remember that associative word or concept, they know where it is. Okay, so you drop your key on the table and you associate it with uh, a rectangle. So when you are looking for your key, you think of a rectangle, then you remember, okay, it's on the table. That is just a very simple way of saying that is how hashing works. Yeah, okay. So dictionary is very important. Okay. Reference books, Wikipedia. Uh, for those who talked about encryption, that's why I have the Bitcoin logo here. Okay. You see how that is related later on. Then, how many of us used shorthand? It's not common these days. Okay. I'm not sure it's still being used. Okay, yes. Yeah. But shorthand is a form of hashing. Okay. At an individual level where uh in class, your fast speaking teacher or lecturer is talking and you're trying to keep pace, you can't write the whole word. Rather than write Britannica encyclopedia, you just write Brit and ENC. Then you move on, you use some weird writing. No, individuals have those kind of shorthands. Like at the end of the lecture, if you ask somebody, hey, can you give me your jottings? Their jottings don't make sense to you, but it makes sense to them. That is hashing. So they've just hashed their their notes. No, okay, so it's the same way hashing works. Okay, hashing is an important concept in not just programming, but computer security. Okay, and not just even before we get to computer security, its major proposition is search. Okay, getting an element, looking for an element without searching. And you see how this makes sense. Note that word, searching for an element without actually searching. So hashing is a process for generating a value from text or a list of numbers using a mathematical function known as a hash function. Okay, so this is very, very important. Is it requires data transformation. Okay, you take a set of input, you run a function on that input, and then you get a value, a digest, a hash code. You see all those terms later on. You get a value which helps you locate that term later on when you need it. So your shorthand, okay, is like opening a dictionary. You're looking for a word, then you open your dictionary, you know where to go to because there's an order in that dictionary. It's a key value pair, and things are arranged in a particular order. So if you're looking for a particular word, you just go to the alphabet, the base alphabet, the first one, the second one, until you get to a particular place there. That still doesn't exactly reflect hashing because hashing is faster than that. Yes, hashing is very, very faster than that. In that, once you get a hash sum, when you get your hash locates your item instantly. As it tells you where to go to. It's not searching, it's not looking for it. So it's like you having a mnemonic, something to use to remember that you put your key on the table. And when you need your key, you are not going to the chair, you are not going to the other rooms where you think it may be. You know where it is, you just walk there. That is how hashing works. That is the biggest proposition and value from hashing before it begins to have uses in security, password verification, and other. Okay, so hashing is a very important concept for hashing. The problem with an array, if you are trying to look up, search for an item in an array without using index, if you use index, yes, very fast. But if you are going to do a comparison, a textual comparison, you want to look for some words, you begin to traverse the array and checking, is the value at this index equal to the value at this equals to this value? Is the value index, is the value equals to this or that? That comparison takes time. Okay. Hashing bypasses that. You do not do comparison. You just go to where the data is using the index. So using hashing for search is very, very fast. So hashing is a technique for efficient data storage using value transformation. Remember, you take a key, which is your value, take a key, transform it, gives you a code. Okay, that code is then used to store your value in a particular index. We'll see how that works. So your key or string of character is transformed to another value. These values usually are fixed length. Okay, so arbitrary size of data. Okay, in that you could have three letter, more than that here, or three characters, more characters, different characters. But when they are hashed, the resulting hash code are all of the same size. Okay, so that's what we mean by uh, mapping arbitrary size to a fixed length data. Okay, and in doing this, uh, what the transformation help us do is helps with fast data insertion, deletion, and retrieval. Oh, okay, so that even when you want to insert object, insert a new value, uh, you just go to the location and then insert at that point, delete at a particular point. Okay, so it's very, very efficient for this. We'll talk more about computer securities and techniques, security application and security techniques later on. Okay. Then when the values are mapped to a fixed length data, we call them hash values, hash codes, digest, or hashes. So depending on where you're reading, you see any of these things used. Yeah. So the hash values, what the digest you get is then used to store your data in an array. Oh, okay, so under the hood, the hashing involves maintaining a hash table, which we'll see later on. Some mention key value pairs, yes, which is very, very important here, especially if you have a concept of dictionary in mind. Okay, your key is used to locate or store your value in a particular place in memory. Okay. And I mentioned before that iteration loop statement in hashing, okay, have no place. It bypasses this. Okay, there is no need to do string comparison as you search for data. Is this equals to this? No. You just get a hash, go to the index, and you get your data. So while hashing is very useful, very fast, unlike heap, is not recommended for finding minimum and maximum elements in a data set. Okay, it's not meant for that. Okay, it's for pinpoint location, hitting the bull's high. Okay, but not for determining priority queues, parent-child relationship, no, that kind of thing. No, you see it being used for data integrity, digital signature, password storage, or password verification, a lot. So it's an important concept that you should be aware of. All programming languages have out-of-the-box implementations or libraries supporting hashing, including, I didn't mention, heap data structure. Then looking at how it looks like, okay, in memory, think of it this way. You have a set of values, okay, and then you want to store these items in, in your application, and you want to store them for efficient retrieval. Okay. And you also want to ensure that they are optimized for quick insertion, deletion. So that is why you want to ensure in this case, in this particular case, you think about this utility as like applying a hash function. So you want to store this value, you apply a transformation on each of the values, which gives you hashes, codes, digest. Okay, it gives you a number. So in this simple scenario, I'm just representing them by 0, 1, but think of it as hash code like this. Okay, so it gives you a hash for that. And once you have that, the hash then you maintain a table. There's a table maintained in memory. In this case, a simple array which says, okay, based on the hash of each value, we use that hash to store them in specific position. So Mexico here, if the transformation for Mexico gives us 0, so Mexico is stored here. If transformation of Botswana gives us 5, then that is stored here. So later, if we want to get Botswana, rather than iterating and checking from index 0 to n, is what is on this index equal to this, is equal to that, is equal to this. Rather than do that, what happens here is that your application takes Botswana, compute a hash function for Botswana, get the hash code, and then use that to just get Botswana here. So there is no search involved. It just goes straight. So it uses the hash code to insert, okay, at a particular location. To delete also, he uses the hash code to, he computes the hash code, then get the object at that location and remove it. Okay, and to retrieve again the same thing. So this is very optimal for this kind of scenario. And again, just to elaborate on what I've mentioned in that illustration, is how it works. It uses a hash table under the hood, okay, designed in most implementations around an array. Okay, like heap, it may be based on array or it may not be. Okay, but this is just to give us an intuition about location. So what this does is, what the primary thing here is that a table is maintained, the hash table. The hash table is a key value pair that stores value against the hash. Okay, so with that hash table, you can easily locate item. So it works with a pair of key value. The key is hashed into a hash function, is hashed with a hash function, and then the result is used to store data in a particular position. So again, it's similar to what we had before. You have variable length data hashed, and then you have resulting fixed length data. Okay, here. So the hash function that is used, that many different functions, okay, many hash functions. But what you use will depend on the type of data you are using as your keys, the kind of data you want to store. This is alphanumeric data. If you are using numeric keys or numeric data, there's usually this modular hashing that is used. It just getting the modulo of a division. okay, the remainder from a division, especially if the numbers, uh, if you are dealing with numbers, okay, and in this case, you have to ensure that, uh, we'll talk about that later, your hash table meets a specific condition. Okay, so the hash function depends on the type of data, whether it's numeric or alphanumeric. Alphanumeric is uh, usually more complex than the numeric, because with numeric, just arithmetic computation uh, mathematically will give you the hash faster. And then the hash function has to use a unique, has to ensure that unique keys are created or unique codes are created and maintained. Okay, in doing that, collision as much as possible is avoided. The challenge here is to avoid collision so that two values don't map to the same hash. It happens, yes, it happens, and there are ways, there are methods, there are functions to not just avoid that, but manage that where it happens. There are suggestions for managing it, but it just happens. As much as possible, you want to avoid it anyway. So again, the key is marked to a number if it's numeric in the range of 0 to n. Okay. Yeah, this challenge is very, very important. I think this is best illustrated. The challenge of hashing is to ensure that your keys, your hash codes are evenly spread. Let me illustrate this by just do this quickly. So remember we say you have a table, you maintain a hash table containing your key value structure. Yeah. Oops, should I need this too? Okay, so uh, your hash table is what stores your values according to their digest, that is, according to their computed hash. So you can say Mexico is stored here, another thing here, another thing here. In this, let's say this is the hash code, this index, this, and the challenge first here is determining the size of this table. How long, how uh, deep, what should be the size of what should be the size of the table, okay, depending on your data. If your table is too large and you are only storing few data items, it's possible you are going to first have a lot of space wasted, not used, all this space. So if I'm only going to store 3 data and I have this length of array, hash table, just storing this. So because this array is created in memory, I just have free space, unused space, reserved in memory, not used, not storing anything. But more than that, that's one problem. You have to avoid that space. Another problem with maintaining a hash table is going by this to evenly spread the keys in the table. So these are our keys. We have them. Imagine that based on the resulting code I computed for these 3 and I got these values close to each other, and I computed for another set of value, and I have maybe this is index 200, and I have this data index 500, I have that data. What happens here is that we have a lot of space. Uh, let's just put it like this. We have a lot of space in between those data. This is not optimal. Sorry. Oops. This is not optimal. We are wasting space. And this will not help us with the caching techniques that is much more efficient for, especially for array. So, because at some point, depending on our caching size, if we want to get the 200 item, this will be slower than if we are getting something close, like in three, you have a value here. If this value is here, it will be much more faster. So the challenge here is like saying the gaps in between your items should not be too much. So the keys computed by your hash function as much as possible should be close together. Okay, that gives you advantage of caching. That gives you an advantage of appropriate space used in your system. Okay, it will also make your search very, very fast. Okay, it's like another way to put it is like saying, don't reserve 1,000 memory location just to store 400 items or just to store 100 items. So you are going to have a lot of gaps. Okay, even if you say the justification is to reserve space for future insertion, okay, each data should be close to each other, such that if you have 1,000 reserved in memory, if and you have 100 items already added, as much as possible, those items should not be far away from each other. And as you are computing much, as you are imputing more values, they are taking advantage of the space, of the extra space. So it's usually advised to give thoughts to your hashing. Okay. For your purpose at this stage, don't worry, you are not going to probably come up with a hashing function, okay? But it's good you note this, you picture this, you have an idea of this in your mind, especially with hashing. And I will show this shortly, okay, just so that you can see how it is. Okay. Basic operations, they include this, okay, getting number of items. Your hash function is very, very important. Yeah, very important equation here, okay, where you have where you have to answer the most important questions here, that your function can compute your hash efficiently, okay, efficiently and timely. Shouldn't be too slow. Okay, though for some hashing function, they intentionally introduce memory block or complexity. That's in security application. Uniformly distribute the keys is important. In some cases, your hashing should work one way, such that from the hash code you cannot trace back the data, so that once you have the hash code, you can say, oh, with this hash code, I can decrypt in quote and get to the actual value. No. So, because some functions allow it, but what is usually advised is one way. Setting an item, inserting an item, then these are basic functions that you do in your exercise. I will skip this. I've actually mentioned it has to do with determining the size of your hash table. Okay, if you are for modular hashing, when you are dealing with numbers, determining the size is important. So some will say you make your table size more than 137, a prime number greater than 137. Okay. Again, it depends on the number of items you intend to store. We've mentioned some of these things. Because of time, we won't go so much into this detail. These are just some simple hash functions. There's a link in the reference for you to go through them. Okay, you could try some of them out in the exercise that you will do. Just simple stuff. Even you can choose any of these division method or formula for coming up with your hash function. Division method, mixed square, folding method, multiplication method. The simplest one is just this, which is the remainder of a division between two numbers. Oh, okay, so K modulus M. Okay, you use that. I will show you an example shortly. Okay, I think I should show you the example here. Let me share. Let me stop and share my screen. Okay, so Windows. I'm looking for, where's my window? Okay. Can you see my Visual Studio code? Can you see my IDE? Let me know. Oops.
No, we can't see it. No.
Oh, someone says yes. Can you see it?
Yes.
Oh,
I
you
can
can
see
see
your
it
screen, but
now.
I'm not seeing your ID. Yeah, I can see your screen, but not
Okay.
your ID.
Okay, let me just share. Okay. Let's share. Oh, okay. I think I did it the wrong way. Okay, my bad. You should be able to see my ID now, right?
Yes, that's right.
Okay, good. Okay, so here's a data hash table implementation. Okay, so a typical example of the ADT, abstract data type of a hash table, where I have a set of functions and maintain a collection, an array structure. Remember, hash table maintains, not in all cases, a hash, an array to store the item. So I have this variable to store a collection of 137 items in this case. I have my simple hash function, which I will show. Then this will show all items, put an item, get an item from my table. The important operations here will be the hash function. So this is a simple hash function, nothing complex. It's just to show how this works. Okay, so for this hash function, we expect your value to be given data, and then the algorithm for this is just to sum the character ASCII codes. Okay, we sum the character ASCII code divided by the array size. So when we sum it, we get a total of all the character code. Then we divide that by 137 or whatever the size of your array is. The remainder you get in this case is your hash code for this simple scenario. Okay, it's the same thing you're going to do, assuming I'm going to use this division method. All right, I will just come here and say my hash function. Okay, maybe I have another function, division method, get the data, and then return okay, k modulus m, where m is our array size. So if this is a data, if this is numeric data, it will work. If not, it will be divided by table length, table size. Oh, okay. So in this case, it's a hash function using this division method. Very simple method. It may not scale for large data size, but just very, if you have a simple set of data and you want to maintain a hash table, yes, you could use something like this. So this is this hash function. And this function is called at the point when you impute data into the system. So if I'm going to add the data, the new data, look at what happens here. I compute a hash. Okay, I run this to get a hash. In this case, it gives me a position, and I use that position to store the data. That, okay, based on the value returned from the simple hash function, I'm storing that data in this particular array index. And if I'm to get the data, again, I compute a key. If I'm given a key or a data, I get the key, compute it, and then return data at that position. Yeah. So that a simple test of it for things like this would be, I have a set of names, okay, and then for that names, what happens here is to instantiate my hash table object, and then insert for each one of them, for each object or value in this collection, I add each one to my database. I call this database in this case. I add it to the database, but in adding it to the database, under the hood, the put function computes an array, computes to get a hash, and then use that to store the data. So that's what happens under the hood. So if I print out this, I will see all of them. And if I want to get value for mine, I just do get, and it returns something like this. Okay. So this is this is the output of the system. Okay. But if you look at this now, if you look at this, I'm printing the index in the array where each name is stored. So based on this, you can see that Cynthia is stored in index 35, which means, okay, this is in ascending, descending order, ascending order. So this means that index 0 to 34 is not filled up. All right, is empty. Index 135 to 137 is empty. All right. For this simple hash function, this is not, the keys are not evenly spread. Okay, they are not evenly spread. But this is just to show how it works, that this is how a hash table maintains the data. So if I'm going to get this data, Mike, to get Mike will mean going to will mean going to computing a hash for Mike, get the index, and then return it. You can see no search involved. You just hit the bullseye. Okay, so this is how hash works, especially in your programming, whatever ID, whatever language you're using, you can use the hash object to practice, but note that this is how it works. This is all about hash or hashing. The major thing again is just the hash function. Oh, okay, so your hash function could return, in this case, an index. I'm just returning an index. It could be alphanumeric fixed length data. Okay, and if you use your programming language hash table, it allows you to store those alphanumeric hash codes uniquely in the hash table object. Okay, and that is also very, very efficient for whatever application you are building. Yeah. So with that said, let me go back to this. Okay. So that is just to show you the aspect of hash function. Okay, whatever you use, you could use this, you could use that. You can just experiment with them. Different algorithms, these are simple, but different algorithms. And if you come here, you see much more complex hash functions that are used in your day-to-day applications you interact with. You must have come across things like SHA functions, SHA, with their various variants, CRC, different hash functions. These are much more complex hash functions, but are used for security. Your secure transport protocol like SSL, TLS using SHA-2, and then other improvements on it. You have this CRC for checking data integrity, okay, to ensure that a particular data has not been tampered with in transport, okay, maintaining the data integrity. You have some MD, you must have heard about MD5, though it's not commonly used again because of problems with it. Okay, so you have some like SHA-3 or Blake2 that are used also in crypto mining. Okay, this is just to show you common hash functions that you may not look at their implementation, but know that it was as simple as this. Of course, they require more steps. This is just one step. This is just K multiplied by K. Okay, then you return the middle digit. Okay, just maybe 2 steps, a couple of steps here and a couple of steps here. These functions require much more steps. They are much more complex, but they generate codes which are unique. Some of them have been broken. Some of like the ones that have vulnerabilities, okay, or the ones that are no longer used or recommended. Okay, so just to give you an idea, just to put this in context, that they have applications in security, in password verification, in digital signature, and general data verification. Okay, but much more important is that, of course, why are they using this security application is also because they are fast. Yes, they are fast, secure, generate unique keys, but they are also very, very fast. Then one last thing I'll quickly mention here, just before I move over from the application here. If you're building a simple application that requires storing password, user's password, don't store your password in simple text. Okay, the actual text, we discourage that. You don't store them in these days in just an open text. At best, take advantage of the fact that there's something called hash or hashing. Okay, hash the password, and then you store the hash in the password column. Okay, which means that later, if you are going to check if the username and password match, you get the username, then you compute a value for the password. You get the password, compute a value, and if that value matches the username and the hash in your system, then you have the right person. You can say authentication was successful. Okay. At times, this requires the concept of sorting, like adding sort to the password or to the username, usually to the password, to generate something much more unique. But something for you to think about and use. If you are not using a framework or an SDK or library to manage your users, maybe Auth0, .NET identity, passport in Node.js. If you are not using any of those authentication mechanisms, at best use hashing to secure your user's password. It will save you some legal troubles later on. Okay. No matter how simple it is, just use it. Okay, so we are rounding up. This is just giving you different patterns. We mentioned this in the course of the talk. Patterns on heap. You see the patterns on hashing. We mentioned them, cryptography and all. Then key skills, you should also still focus here. They are recurring thing. All right, as we move along, indexing is still important. Item swapping is still important. Your data processing, then recursion. Okay, yes, discouraged, but in the context of heap, you may have to use it for swapping. You could use it. I've seen implementation that avoid recursion altogether and uses iteration. Oh, okay. That also works, but because you already have the advantage of a less time complexity. Okay, so recursion, just know how to use it, understand that it's relevant in this discussion, and then alternatives as well, which is iteration. Then the problems we are looking at in this next week is let's do this. Heap, create an abstract data structure for a heap to contain these functionalities. Okay, let's look at it together on your GitHub profile. The same for hashing. This is important. Just do this so that by the time we go into our algorithm, we can be borrowing some of the data structure and concept, okay, to solve certain problems. Okay, so these are the things I look forward to in seeing in your GitHub link in the next few weeks. Okay. Thank you very much, everyone. You see further resources, once additional reading and much more information about this once we share it. Okay. Okay. So, any question? Okay, I see a question here that I thought iterations loop statements are used to search through hash map if the key is not known. Okay. Oh, if the key is not known, why would the key not be known? It's not optimized for search iteration. iteration is not meant to be the value of this utility. No, okay. I've seen implementation where if you search for a key and the key, there's no value return, you could search the next available location or index. That implementation is relevant in the context where you have duplicate keys. So only where there are duplicate keys or possibility of duplicate keys, you do what is called linear probing. The linear probing is that you get something, you don't find it, then you begin to check other places in the memory. Okay. Or if you are going to add a new item and that item gives you a code, a digest that already exists, that is, there's a data already occupying that place. So that's a collision. However, you can still store this data. So some people will use linear probing to store it in the next available or free space. All right. That now means that when you do a search, you have to do iteration. A bit more complex and convoluted, but not advisable. But in some cases, it's done. Yes, it's just done. That's what I can say about it. And then, okay, what other question? And programming languages that handle garbage collection and memory management not handle this? Okay, where Lumide is asking this, but I can't remember the discussion that led to this question then. What was I saying then at the point? Okay, but if not time, we can actually, you can put it on the Slack channel and then we discuss it further. No, okay. Okay, we'll take you more time. If there is no other question, we can call it a day, and then I'll share this. I look forward actually to see your implementation. Yes. So thank you, everyone. Over to you. Let me stop sharing.
Thank you so much. Thank you so much. So that was an amazing one. Really learned a lot. Want to thank you and appreciate for your time as usual. Thank you so much for all that you do for us. This has been an amazing session. I learned a lot, and I know a lot of people learned a lot. So also, I've also posted the feedback form in the comment section, so you can actually drop your feedbacks. And thank you so much for the participants for joining. And catch you up next week. Bye for now.